the degree of the length of the list of the first list. Whereas if you have a linear search on a sorted list, then you actually have these two-pointer kind of thing that you're going to be moving. So it's hard to parallelize it from the from the thread point of view. So you're going to need to have essentially doing parallelism at a higher level. So you need to find parallelism across all the edges rather than parallelizing it within one edge when you try to find an intersection. So there's no real parallelism in the finding an intersection for each edge. So you're going to be forced to parallelize at the edge level. Okay, so that's those are the kind of trade-offs that you're going to see. So let's go through one of these. Let's assume that we're going to have a CSR representation. So this is essentially the same representation that we talked about for breadth first search. Okay? So I have a graph here. I have the adjacency matrix. So this adjacency matrix, I'm going from the smaller number to the larger number to the direct graph. So I have a upper triangle matrix, and then I do a CSR compressed row representation. So this row has 2 elements, this row has 3 elements, and so on. So the beginning location of the 0th row is 0, and then the beginning of the next row is 2. That means that the first row has 2 elements. That's right, these 2. And then this guy starts from here, the next one starts from here, so the next row is here. Right? And then you have the next one, the next row here, and then 8, you don't have anything here. So that's why it's 7 and 8 are both pointing to the same place. So you don't have anything in this. So this should be, this actually 7, and then the 8 should be 0, right? So you have one more for this guy, and then 0. So for edge 0, 1, edge 0, 2, and then this is edge 2, 3. So the way to read this is you start with this. This gives you the row index, right? This is the row index. You use the row index to count here, so that also gives you the source ID. And then this is the destination index. So it depends on which one you have. It's the source index and the destination, source destination. Right? So let's do some triangle counting with this. I'm going to come back to this point a little bit later. The problem is, if we want to be able to have every thread to pick up one edge, and then do the intersection of the 2 end nodes of that edge, right? If we want to make sure that every thread can pick up one edge, we need to have a quick way for all the edges, for all the threads to come to the data structure and pick up an edge, right? So the problem with the CSR representation is that if I have all the threads to come in and I want them to pick up one each, okay, one each. So let's say thread 0, thread 1, thread 2, thread 3, thread 4. How do I find the source ID for the edge? Right. So if I just have all the threads to come in and pick up one of these, I have the destination, right? The thread needs to also find the source. So the way the thread could find the source is to do a binary search, okay? Because let's say the thread is picking up, let's say, this guy, okay? This guy, and this is in the third of 0, 1, 2, location 2 here, right? I know the destination is 2. I want to find the source ID. but I know I'm in location 2. So I'm going to go back and do a binary search and find the 2 numbers in between which I exist. So this is actually going to be between these 2 numbers. And then I know that my node, that my source ID is actually 1. Okay, so this is a reverse mapping problem for finding that source ID. Yes.
But since the CSR gives you like what's the capacity of the real like the data array, right? So
yeah.
why do you have to do that order?
Oh, because in order for me to do the intersection, I need to have the node, my source node and destination node, so I can go and find the neighbor list of both nodes. Right? Going from the node number to the, if I go from the node number to the destination is easy, right? But going from the destination number to the source is not that easy. I don't have that information.
You just keep working on that every single pixel?
Yes, exactly right. Yeah, so that's exactly the reason why, for convenience, we will have both the source and destination numbers kept in this. So it's really what we call the CSR, the COO, because COO essentially gives you both the column and row number for all these elements, right? So you say, okay, if I have COO, why do I bother to do this? Because this gives me a very easy way to find all the neighbors for any node, right? So you really have 2 requirements. One is I want to be able to grab work. When I grab work, the easy way to grab work is to go to this array and pick up one of the locations. But if I pick up that location, the location would not be able to tell me the source unless I store it. If I don't store it, I need to go back and do the search, right? And search is expensive. Questions? Okay. So let's say if I'm willing to have the source and destination represented, I still use the offset pointer, the row offsets to tell me all the neighbors of any particular node. Then I can do something very, very simple in terms of in terms of the work assignment. I can just have every thread to come in, okay, and have every thread to come in and pick up one location, right? So this gives me the source of the source, and this is the destination, so that I can have all the information, and then I can use this to give me the neighbors of the 0. So 0 comes here and say, okay, so these 2 delineates all the neighbors for node 0, and these 2, 1 comes here and say these 2 will give me the node all the neighbors for node 1, right? And I have an easy way to find all the neighbors. So that data structure gives me everything I need for each thread to do its work. Does that make sense? Okay, now. So that's exactly what I'm going to do. I'm going to distribute the work. Let's say, I may just cut this way for the thread blocks. So the thread blocks will take, a partition. And in some cases, people even have multi-GPUs. They would partition the work across GPUs by cutting these source and destination array, into sections. And then, they will still need to use the row offset to be able to find the destination list of each of these nodes, right? The neighbor list of all the nodes, of both the source and destination nodes. So that's how we find these, right? So I draw them essentially in the separately, but these 2 are the same thing, right? Just so that I kind of unfold it so that you can see it more clearly. Make sense? Okay. So let's go with this. So this is essentially the outline of your kernel code. So if you have a kernel that's going to the thread, each thread is going to find all the intersections for one edge. So each thread is going to come and pick up a pair of this. So that's why we have these different colors, right? Each thread will pick up one of these pairs. So then the thread is going to say, okay, the source is 0, the destination is 1, or so every thread is going to pick up one of these pairs. So let's just pick one of the threads. Let's say thread 2. It's going to come and say the source is 1 and destination is 2. So this is 1, 2, right? Edge 1, 2. 1, 2 here. 1 has several, one has neighbors. So 1, you go back to the pointer 1, and then you say, oh, it starts with 2, right? It starts with 2, and then with the 2, you go and see the section. So that gives you 1, you go here, 2, you go here, and then so these pairs gives you this pair and this pair gives you the section that gives you the neighboring edge or outgoing edges for those two nodes. So in the code, this is exactly what we do. So the thread is going to come into data structure and find U and V, right? U and V. In this case, it's the 1 and 2. And then we're going to access the P, which is the row pointer or row offset array, right? So we use the U and V to access the array to give us the starting pointer, right? The starting pointer of these neighbor lists. And then we go into the intersection mechanism. Okay? So we say this. We ask the question. Okay? So for this guy and this guy, we're going to have two sections here. So this guy is going to start from here, okay? And this ends here, right? So this is starting 2 and then here. The other guy, the B pointer will start here and then here, right? So it has this. So we're going to start with this guy and this guy. We're saying, okay, this is smaller than this one. So this guy is definitely not an intersection, right? This guy cannot be intersection because this one starts with 3. So 2 there's no chance, right? So you increment the pointer. In this case, I say, aha, I have a 3 match now. So now I have an intersection. But it may well be that this guy is so much bigger than this guy, you need to keep incrementing it, right? Until you match this guy. Or in some cases, you could actually, after you may end up in a situation where you may need to come and increment this guy. Let's say 3, you find the 3, come on, and then after that, this guy may be bigger than this guy, so you may need to increment the other side. The point is, you will never need to go back and re-increment. You can just keep going, and one will be bigger than the other, or so then you just keep incrementing, or you see it equal, that means you have a intersection, right? So you can finish this by scanning through the 2 lists, and it's the sum of the list, right? The 2 lists gives you the computation complexity of this. It's very, very efficient. You only need to go through the list, each list once, right? But sometimes you increment one, sometimes you increment the other, until you find this equals, and then you keep doing this. So this you will find, you'll begin to realize at some point that this is actually very similar to the merge sort algorithm. Okay, these two are extremely related. So we're actually going to have a lecture on merge sort. Any question about this process? You have two lists, and the two lists will have a few equal numbers, right? And then you start at the beginning of each list, and if they are not equal to each other, there's no match there. So you increment the one with the smaller number to the next position, and so on, until you either equal or until that guy passes, right? The guy could also pass this other guy, right? And then you need to increment this guy to catch up. So you just keep incrementing until they equal or they pass each other. You turn the other one until you finish scanning both lists. So the computational complexity is going to be the sum of these two, the length of these two lists. So this is the algorithm, and so you do the intersection, and then I say, hey, you know what I have. It should be just try it. Yeah. Okay. So this is here I want to make another observation. This method works well when the two lists are about the same size. Okay. And and also they may not be very long. So if you have a situation where these lists are extremely long, okay, let's say if one list only has 2 elements, and the other list may have 1,000,000. Okay, the thread will be iterating through a large number of elements, and this means that you may be better off if you try to exploit parallelism, right? Scanning through 1,000,000 elements in one of these GPU threads is not that fun. Okay, so when you have a situation where one thread, there are a few elements in one list and a very, very long, the thread, large number of elements on the other list, this is actually a prime candidate for binary search. A better way to do this, for that situation, will be take one of these, elements from the smaller list, and then do a binary search. Okay, do a binary search. But hopefully, 1,000,000 elements only will take no more than 20 iterations, right, for binary search. Meanwhile, you take the other element, right? You take the other element and also do a binary search, right? And it will end up in somewhere else in that list. But this is totally parallel. So you can use 2 threads, and each thread will be doing a binary search.
Can we do the same for short arrays?
For short arrays, is seldom, if both arrays are short,
yeah,
it's much better if you just do the sequential. If one is a very, very long array and one is a very short array, that's when it start to get dicey. But if you have 2 very long arrays, then it also becomes a little bit weird, because basically the computational complexity of the binary search is the number of elements in the shorter list times the average number of recursions for that binary search, right? So it's log n. So it's actually n of the list and the log n of the other list, right? So if one of the lists both of these are very, very big, that's not a very good thing either, because that n log m maybe could be bigger than n plus n. Okay. So these are the tricky parts that make graphs, algorithms extremely hard to design, because you need to switch algorithms if you really want to get good performance. And if you're not careful, your algorithm sometimes when you hit the back data, the pattern, then your algorithm will run dog slow. Okay, and it actually happens. So, for example, if you go on Facebook and analyze it, chances are you will see this kind of situation. because there are not too many very long lists. You know, I would say probably Brad Pitt and Angelina Jolie. You know, that tells you my age. So whatever equivalent version of your generation. So then, you know what? So if you try to find a triangle between Bonnet Hu and Angelina Jolie, you know, you will take my neighbor list and then take Angelina Jolie's list and then do a binary search on Angelina Jolie's, right? So, you know, unless you take Angelina Jolie and Brad Pitt, the two lists together and try to do this, you know, the binary search will be better. Okay.
Yes, one more point. So in binary search, your data access patterns may be far away from each other.
Yes.
In the linear search, the caching effect may be like boosting.
Yes. Yes. Yeah. In fact, that's exactly right. So that's why essentially what you don't want to do too many steps of the good thing about binary search is that you're only touching a very small subset of the locations. So if you are forced to go through the entire entire length, you need to have the memory bandwidth to bring in the entire length, right? So even though you're branching far away, as long as you're only bringing a small portion, touching a small portion of your data, you're okay, right? But if you start to, but the problem is if different elements here start to touch very different sections in that their binary search will start to have trouble. Okay. So this is the reason why these algorithms, oftentimes you will see some really complicated sampling of data and then try to the switch algorithm and so on into the best analytics practice. Okay. Any other questions about this? This is good questions. Any more questions? Okay. So congratulations. So we now have a simple, triangle counting code, and so this is the kind of the basic version that you can work with. So for your NP, this will be the basic version. Okay. If every thread will pick one edge, and then it will take use the pointer, the row pointer array to pick up the section, the two neighbor lists for those two endpoints of the edge, and then you do the linear scan, right? The linear scan, the one passing the other, and so on. Find all the intersections, and then you find the triangle involved with that pair, right? And you add up, you do a global sum of all the triangles you find. That's the basic version. If you bother to switch to a binary search for some of for these very uneven distributions, give you extra credit. Okay, and if you find the multi-GPU, so I'm going to probably show a couple of possibilities, and then I'll show you some interesting challenges in multi-GPU code. Then you get even more extra credit. Okay. So you can, this is something that you can spend a whole semester on. Okay, and these two people can tell that. These three people can tell you, right? Yeah. So but it's really you can learn a whole lot of things from these kind of experiments. So depending on your time, you'll get almost the full credit for doing the base version, and then I'll give you a little bit extra credit and a lot of pat in the back if you do the other version. Okay. Okay, good. So I will see you on Thursday.